The only show that rips apart the research papers, the proprietary notes, and the foundational academic texts so you don't have to.
Yeah, that's right.
Our mission today is, well, it's pretty profound. We are moving beyond the traditional, rigid mechanistic view of the athlete as just a machine of levers and pulleys.
Right.
And we're seeking to understand performance as what it is, a complex adaptive system. And this framework is it's absolutely crucial for understanding why that textbook technique you drill all week often fails the second any real pressure is applied.
It really is.
We are diving into a stack of truly challenging source material today. I mean, we're looking at the groundbreaking work of Arthur Iberol on homeokinetics, plus some really foundational concepts from ecological psychology and even the rigorous mathematics of dynamical systems theory.
And this dive couldn't be more timely because that old reductionist paradigm, the whole idea that you can isolate a skill, optimize that one single part in a vacuum, and then just flawlessly stitch it back into a game.
Yeah, it doesn't work.
It's fundamentally flawed when you're talking about high-performance sport. The real world demands convergence. The chaotic, the real-time integration of biomechanics, physiology, and psychology in a game environment. It demands a model that actually accounts for that chaos, not one that just pretends it doesn't exist.
Right.
We are looking for a more resilient understanding of skill, one that doesn't just shatter the moment the environment changes. So if you are a coach, a trainer, or an athlete who has ever watched a practice hero become a game ghost, well, this deep dive is for you.
That's it exactly. Our mission statement today is this. We're taking the foundational science, Iberol's homeokinetics in particular, and we are translating it directly into the coach's playbook.
Yep.
We're answering the fundamental questions about how these concepts translate into skill acquisition, training design, and, most importantly, winning performance under pressure.
Let's do it.
Okay, let's unpack this. We have to start with the foundational question, right?
Mm-hmm.
What exactly is this framework, and why do we need a new word for it? So explain it like I'm a sport coach, not a physicist. I get muscle recruitment, I get recovery. But thermodynamics, what's going on here?
Absolutely. Let's start with Arthur Iberol and his theory of homeokinetics, which he developed with Harry Sudak back in the 70s. And, this isn't just a philosophy. It's a serious attempt to unify physics and biology.
Great.
Homeokinetics is described as a generalized thermodynamic approach to complex systems. It's really trying to ground all complex behavior, including ours, in common physical principles, things like energy flow and how materials organize themselves.
So how does that apply to my athlete on the field?
Think of it this way. The core idea is that all complex systems, whether it's an athlete or, even something non-living like a hurricane, they're all composed of what they call atomistic-like units bound together into interactive ensembles. Right. And these ensembles form nested hierarchies of organization. So your athlete isn't a simple machine. They are a nested system of systems.
Okay, break that down. Nested systems.
It means you've got molecules, muscles, organs, intentions, neural firing patterns, all of it, coordinated and embedded within an environment. And the key focus of homeokinetics is what's called vertical integration.
Vertical integration.
The up-down processes that bind all those different levels of the system together.
Okay, so let's make that concrete. The connection from the micro to the macro. Give me an example and a play.
Okay. Consider a runner system late in a game. At the lowest level, you have molecular activity, right? ATP consumption, calcium signaling in the muscles.
Got it.
A level up from that, you have muscle fiber recruitment. A level above that, cardiovascular regulation, breathing, all of that. And then at the highest level, you have the psychological state like, say, anxiety about the opponent catching up. That anxiety acts as a high-level constraint.
And homeokinetics is about how all those levels talk to each other instantly.
Exactly. It's interested in how a constraint at one level, say, that high-level competitive anxiety, instantly triggers changes everywhere else.
How so?
Well, that anxiety triggers physiological changes, right? Increased cortisol, your breathing pattern changes. And that immediately feeds down to alter low-level muscle stiffness and joint coordination, and that could change your ground contact time.
Right.
The whole system coordinates across all levels, all at once, just to deal with that anxiety, which means the movement pattern itself has to change.
So that movement variability I see when a player gets tight, that's not an error. It's actually a necessary systemic response to the stress.
That's it. You've got it. The system is always seeking a temporary, viable balance under all these shifting demands, and that's why this framework is so powerful.
Okay, so if I'm a coach listening to this, and I only remember one thing from Iberol, what is it? What's the single most important takeaway?
It's this one sentence. Performance is an emergent phenomenon. It arises from the interaction of all those many nested subsystems and the environment. It's the integration of processes across all scales, from the tiniest neural signals all the way up to the social context of the game. You can't understand the output, that beautiful, powerful movement, by only studying the input from the brain.
The movement emerges.
The movement emerges from the entire system interacting with its constraints.
Now, here's the skeptical voice. I hear this from coaches all the time. This sounds like really fancy language for context matters.
Right.
We've had systems theory for ages. Every science knows that parts interact. What's actually new here? Is this just systems theory with a new label? Where's the promised physical rigor?
That's a critical challenge, and it's a fair one. The difference, though, is in the foundation. Homeokinetics provides a physical basis for this thinking, which, a lot of generic systems theory can lack.
A physical basis.
Yeah, Ibril and Sudak were trying to explain how these systems organize themselves using concepts rooted in physics, specifically non-equilibrium thermodynamics. They argue that complex systems, humans included, are constantly dissipating energy and maintaining these stable yet temporary states that are far from equilibrium.
Okay, you're losing me a little bit.
Stay with me. To do this, to stay stable, they rely on fundamental physical principles like limit cycles and oscillations to generate patterned functional behavior. The rhythm of walking, the cycle of breathing, that's not just a neural program. It's a physical necessity for a complex system to maintain itself by managing energy flow. It offers a physical foundation, as they say, for Gibson's theory of perception and action.
So the reason my athlete moves rhythmically isn't just because their brain sent a command, but because their entire system found an energy-efficient, stable, oscillating pattern that just works.
Precisely. That oscillatory pattern is the system's preferred, most stable way to function under those constraints.
So what problem does this solve that traditional biomechanics, plus physiology and psychology, don't already cover? Why do we need this new framework?
Because the traditional mechanistic models, they fail spectacularly in one key area: context dependence. They assume a simple linear cause and effect. They believe that if you optimize a joint's function, maximize its energy, and stabilize the athlete's intent, you get the perfect performance.
That's logical.
But it ignores the nonlinearity that emergence requires. It assumes the same ideal technique applies everywhere. It isolates parts, measures them against these idealized average patterns, which are they're doomed to break down under the pressure and novelty of a real game.
Give me the shortest, most visual example in sport where that classic model just completely fails.
Okay, the tennis player's forehand. In a controlled drill, a ball machine feeding perfect, predictable shots, the athlete can execute a stroke that looks textbook perfect. Every joint angle is pristine, the coach is thrilled.
I know that drill. I've run that drill 1,000 times.
Right. Now change the environment. It's match point. The opponent hits a wicked slice serve that kicks up unexpectedly. The player is gassed, running wide. To get that ball back, they have to deviate from that textbook form. They might drop their elbow, change their grip weight, take an awkward step.
And the reductionist coach, watching the video later, circles that deviation in red ink. Error. Fix this.
Exactly. That's the failure. They label the deviation an error. But the field-based ecological analyst sees it totally differently. They see that deviation as a necessary adaptation.
Adaptation.
The system made it in real time to maintain viability. The player traded perfect form for functional stability under pressure. Viability here is just the system's ability to get the job done, get the ball back over the net within that hostile, ever-changing environment.
So the ugly shot that wins the point is better than the beautiful one that hits the net.
Infinitely better. If that slightly awkward variable shot works under novel, high-pressure conditions, it is far superior to a perfect textbook form that was too brittle to adapt.
That reframing viability over perfection is a huge shift, and that's where a lot of traditional coaching starts to get really uncomfortable.
Yeah, that reframing of error is absolutely massive. It just flips the script on what a coach should even be looking for. And when I look back at my own coaching failures, it was always chasing that mythical perfect rep.
We all did it.
So if the system is constantly adapting to constraints, we have to ask a really uncomfortable question. Are we training athletes, or are we training a system that includes the athlete, the environment, and the task?
We are training the system. Or, more precisely, we're training the organism plus environment relationship. I mean, the ecological dynamics perspective, which is so deeply informed by this kind of thinking, says that performance isn't a thing inside the athlete. It's not some rigid motor program waiting to be activated.
So what is it?
Skill is an emergent property of constraints, and this is where we have to bring in James Gibson's ecological psychology. He argued that organisms directly perceive affordances.
Affordances. Define that for a coach. An affordance is an opportunity for action provided by the environment, but it's relative to the organism's unique capabilities.
Give me a powerful example.
Okay, think of a steep hill on a bike path. For a price cyclist, that hill affords a high-power interval workout.
That's right, an opportunity.
But for an elderly person with a bad knee, that same hill affords taking a rest break or maybe just turning around. The opportunity for action. The affordance, it's not an objective feature of the hill itself. It only exists in the relationship between the athlete's current state, their strength, their fatigue, their bike, and the environment.
Which means perception-action coupling is everything.
It's paramount. You have to perceive the affordance to select the action, and then the action you take changes your perception of the next affordance. It's a constant loop. So training that decouples sensing and doing, like, say, practicing a pass to a static cone instead of a live defender.
You're creating a less adaptable skill.
Profoundly less adaptable, because it's not relevant to the context of the game.
This directly explains that classic coaching nightmare, the practice hero game ghost phenomenon. I mean, when a guy can do it in training but not in games, what does this framework say is actually happening?
It says your practice design failed. It was a failure of representative design. The practice tasks were simply not representative of the game's constraints.
The athlete system adapted, but to the wrong thing.
Exactly. It successfully adapted its movement pattern to the narrow, sterile constraints of your drill. But when the environment shifted, when the informational variables of a real game like pressure, speed, unexpected movements, fatigue were all introduced, that specific coordination synergy that works so well in practice, it just failed to assemble itself.
Because the information it was built on was missing.
The critical information was missing from the practice tasks.
Yeah.
Skilled performance relies on the system being attuned to key informational variables in the environment in real time. You know, the subtle angle of a defender's hips that tells you which way they're about to break. If your training doesn't include those information variables, the coordination collapses in the game.
So the athlete hasn't learned how to learn under competitive pressure.
That's a great way to put it.
Okay, let's tackle the concept that causes the most friction in coaching. Consistency. Every manual, every coach says consistency is king. But we know from the work of Nikolai Bernstein, the Russian physiologist, that expert movers actually exhibit more joint variability than novices.
Yes.
That feels so deeply contradictory. If technique is variable by design, what does perfect reps even mean anymore? And what's the real difference between consistency and stability in a living system?
This is the absolute centerpiece of the entire paradigm shift. Bernstein famously described practice as repetition without repetition. If you film an expert golfer hitting 100 balls, you'll find enormous variability in their joint angles, their muscle timing, specific force applications. But the outcome, where the ball goes, is highly reliable.
So the variability isn't noise.
It is not noise or error. It is structured variability that allows the outcome to be stable. Experts are exploiting their system's many degrees of freedom to constantly compensate for tiny internal changes, like muscle fatigue or a slight shift in balance, and external changes, like a gust of wind.
So we need to completely redefine our terms. What's the practical difference for a coach between consistency and stability?
Consistency is the rigid replication of form, always hitting the exact same joint angle. We can call this brittle movement. It only works in perfectly sterile, predictable conditions.
Okay.
Stability in a dynamical system is stability through flexibility. It's resilience. The skilled performer develops what we call synergies, these flexible, temporary groupings of muscles and joints that compensate for each other to reliably achieve the goal despite any changes.
So a rigid model might demand technique A, always.
Right. But the system itself might inherently shift to technique B when the athlete gets tired or has to move faster, because technique B is dynamically more stable under those new constraints. So we have to stop trying to enforce a rigid form and instead help the system find a range of functional patterns that are robust to being knocked around.
That's fascinating. You're telling me that a slight technical flaw I might see in a game could actually be the athlete's system protecting the outcome, preventing a catastrophic failure.
Absolutely. The system will always prioritize viability. If you try to force them back to that perfect form when they're under stress, you might just collapse the entire viable pattern they had spontaneously organized.
So we are coaching solutions, not positions.
Exactly. The whole focus shifts from executing a textbook position to finding a viable solution. The ecological approach teaches coaches to ask a different question. Is the athlete perceiving the right information and finding an affordance to achieve the task? That becomes your operational measure of skill.
The capacity for adaptive regulation.
Yes. To maintain functional performance under these ever-changing demands. The goal of practice isn't to eliminate variability, but to cultivate functional variability, a whole toolbox of techniques that work under different conditions.
Okay, this all clicks philosophically, but coaches need to see where this homeokinetic system, you know, lives in the real world, on the field. This idea of the environment as a central part of the system is the hardest leap for most of us.
For sure.
So give me 3 detailed examples where the environment is doing as much coaching as the human coach.
Right, this is the practical side. This is the implementation of the constraints-led approach, the CLA. The coach's job really shifts from being an instructor to an architect of the learning environment. You manipulate constraints to channel the athlete's natural ability to self-organize.
Okay, example 1.
Example 1, manipulating a task constraint. Let's say you're training goal kicking in soccer. Instead of giving a bunch of prescriptive instructions on foot placement, you just change the shape of the goal. You make it much wider, but also much shorter.
Okay, interesting.
That new goal shape, the task constraint, immediately changes the affordances. The athlete is now forced to spontaneously find a different trajectory, maybe one that requires a flatter, lower ball flight. They have to discover an internal coordination pattern to achieve that goal, which they probably couldn't have figured out from you just telling them.
The environment teaches the solution. Example 2.
Example 2. Manipulating an environmental constraint to encourage exploration. For sprinters working on acceleration, you might use a slight decline slope for some of their sprints.
Right.
The environmental constraint, that downward slope, it increases their speed and changes the balance requirements. This forces the athlete system to explore a new coordination pattern, maybe a longer stride, a different arm action, to maintain stability at that higher speed. They discover their own optimal way to organize, rather than being told what their biomechanics should look like.
And a third one, maybe with perception-action coupling.
Okay, example 3. Maintaining that perception-action coupling. If you're teaching passing in football, instead of a sterile drill with cones, you introduce a 2-second reaction window after the receiver starts their route. You add a live defender.
Ah, now it's a game.
Exactly. That time constraint and the defender force the passer to attune to the real informational variables, the defender's movement, the receiver's pace, and integrate the throwing action with their perception. The skill they learn is now viable under pressure.
That's the core of it. The environment becomes the implicit instructor. Now, where do you see those nested systems in an actual play? Break down the layers for me. Say, a fast-running gate at the end of a long game.
Okay, so we have to think about the system's energy flows. At the low microscopic level, that gate is governed by the recruitment and fatigue of neural signals and muscle fibers. As the game wears on, ATP availability becomes a huge constraint at this level.
Got it. The fuel tank.
A level up, at the intermediate level, those actions are constrained by the cardiovascular energy supply. Oxygen delivery. Fatigue hits this layer hard. And at the highest level, the movement is influenced by psychological arousal, tactical decisions, the perceived distance to the goal line, that high-level context.
And the key is that a problem at one level cascades through the whole system.
The whole system. Fatigue, which starts at the microscopic level, becomes a high-level constraint, maybe as a cognitive distraction, which then forces the entire system to reorganize the running pattern. The athlete's form breaks down, not because they forgot the technique, but because the systemic constraints have changed, and the system is desperately trying to find a new, less efficient, but still stable gait pattern just to finish the task.
Okay, so how does this framework explain stuff like momentum swings, slumps, tightness, streaks, without just turning it into, locker room woo?
We use rigorous concepts from dynamical systems theory, specifically attractors and phase transitions. An athlete's preferred successful movement pattern, the one they fall back on, is a stable attractor. The system is comfortable there, it's efficient.
And a slump.
A slump or a streak is when the system shifts from one stable attractor to another one, or sometimes to a highly unstable one. And that shift is called a phase transition.
Tell me more about that phase transition idea.
There's a famous experiment by Scott Kelso on bimanual coordination. Participants were asked to move their fingers in an anti-phase pattern like one moves up while the other moves down at increasing speeds.
Okay.
What happens is, when the control parameter speed increases past a certain point, the system spontaneously and involuntarily switches to the in-phase pattern, both fingers moving together.
That being told to.
So no instruction was given. The system just reorganized itself because the anti-phase pattern became dynamically unstable at high speeds.
And that matters in sports because
Because when a control parameter like pressure or speed or fatigue changes in a game, an athlete's entire system or even a whole team's coordination can spontaneously shift from a successful attractor, like fluid movement, to a new, less effective one, like tightness or hesitation.
So momentum swing isn't just emotional, it's a physical reorganization.
It's the system attempting to find stability in the face of chaos. The old successful pattern is no longer viable under the new higher constraints, so the system self-organizes to the next available stable mode. That might be a slump, but at least it's a pattern the system can reliably execute under that high stress.
Okay, so if I'm an architect of constraints and I change just one thing, the rules, the spacing, the time on the clock, what should I expect to change first? The decision, the movement, or the physiology?
You should expect change across the board almost instantly, because intentions, perceptions, and actions are all intertwined processes. A constraint change immediately changes the affordances available to the athlete.
Which forces a new movement pattern.
It necessitates a change in the movement pattern the athlete has to assemble. It's a non-linear effect. Think about a penalty shot in hockey. Changing the score, a high-level constraint instantly changes the psychological arousal, which shifts the perception of the goal's size, which in turn changes the speed and angle of the shooter's wrist. It's not a sequence, it's a codependent reorganization.
Finally, let's define clutch performance through this lens, without the mythology of having heart or wanting it more.
Clutch is not mythology. It is adaptive regulation in its highest, most refined form. It relies on the athlete's capacity, built through all that varied practice, to access a broad repertoire of viable solutions. The technical term for this is degeneracy.
Degeneracy.
It's the ability of functionally distinct structures or movement patterns to produce similar outcomes. A clutch athlete doesn't have just one solution for a problem. They have many functionally distinct movement options available. And their system has practiced tuning into the precise informational cues of the environment to select the most viable one in real time.
So they're not executing a script?
They are innovating a movement that is maximally stable and viable for that single high-stakes moment.
This systems thinking is compelling, but the coaches we work with, they need proof. They measure everything. In the traditional model, the goal is always high output. Max vertical jump, max velocity.
Right.
What do we measure if the goal shifts to system organization and adaptive capacity instead of just raw output?
It's a huge shift in focus. If the goal is system organization, we have to stop measuring isolated outputs and start measuring traits that reflect resilience, adaptability, and the quality of that perception-action coupling.
Because maximizing one thing can hurt another.
It often does. The system is so interconnected and nonlinear that maximizing one isolated factor can actually degrade coordination somewhere else. So we shift our focus to tuning the coordination pattern across different constraints.
So what are the actual field metrics of adaptability? Can a coach measure this stuff without a multi-million-dollar biomechanics lab?
Yes, absolutely. You focus on the quality of the movement organization. First, you look at functional variability. It's the range of techniques an athlete can use that reliably work under different conditions. A coach can use simple video analysis during practice drills where you're constantly varying the constraints, passing with one defender, then two, then different ball sizes.
And you're not looking for the average form.
No, you're tracking the range of successful techniques. A broad successful range means high functional variability. A narrow range means the athlete is brittle. And a broad range that includes a lot of failures means you got sloppy control.
Okay, what's next?
Second, error recovery. How fast can the performer adjust when the relevant information in the environment suddenly changes? Learning in a complex system looks like faster error recovery, not just fewer errors.
How do you measure that on the field?
You can use a drill that requires rapid compensation, a lateral move followed by a sudden change of direction where you unpredictably change the starting surface. Even just with video, you can gauge the time it takes between that perturbation and when they return to efficient movement.
Okay, and a third metric.
Third, exploration. How much does an athlete spontaneously vary their approach when you give them a new problem? You measure this by just observing. If they hit a plateau, you can implement a new constraint that forces them to explore, like, say, tying one arm down, and then you measure the diversity of solutions they try. Active exploration is a sign of a healthy, self-organizing system.
So how do our existing tools, force plates, GPS, heart rate variability fit into this without becoming the whole religion? Coaches have invested a lot of money in this tech.
They're invaluable tools, but only when you frame them correctly. They give you highly detailed measurements of components force, external load, internal status, but homeokinetics demands that you frame them within the whole system's ecology.
So the GPS data isn't the whole story.
Right. GPS might tell you the external workload was 4,000 meters at high speed. A systems coach asks, how did that load affect the athlete's adaptive capacity and movement organization? Did they maintain their functional variability at minute 80? Or did the system become stiff and brittle? The GPS data just becomes a control parameter to study the systemic change.
So just because you can produce more force on a force plate doesn't mean you're a better athlete.
Exactly. Simply increasing ground force production doesn't guarantee faster sprints unless that force is applied with the right timing and direction, which is something the whole system coordinates in context. You need to look at force application variability. Is it variable in timing but still consistent in the outcome?
Okay, so if you were to design a simple dashboard for a coach that reflects stability, adaptability, and readiness, not just workload, what would be on it?
A simple dashboard would focus on the relationships between variables. You'd need two key metrics: load versus adaptation response. The load comes from your GPS or RPE. The adaptation response comes from those field tests that stress adaptability.
So it would have.
You'd want to see a functional variability index tracking the range of successful techniques in your constrained games, and then your HRV resting measures as indicators of systemic readiness.
And what's a red flag?
A coach wants to see high workload paired with high functional variability and stable readiness. If the workload spikes and functional variability plummets, that's your red flag. The system is becoming rigid, brittle, and non-adaptive. A slump or an injury might be just around the corner.
That brings up a critical question when I'm reviewing film. How do I know if the variability I'm seeing is that healthy exploration, or if it's just sloppy, uncontrolled motor control?
The difference is defined by its function. It's functional variability if it maintains viability, if it reliably achieves the task goal across varied conditions. It's a system intelligently using its degrees of freedom to compensate for perturbations.
And sloppy is.
Sloppy motor control fails the task goal, or it collapses immediately under stress because the system can't organize a stable synergy that works. So if the outcome is stable, even though the form changes, a perfect pass despite a weird arm angle, the variability is functional. If neither the form nor the outcome is stable, it's sloppy, and that tells you that you need a new channeling constraint.
Okay, let's get super practical. If performance is truly a field problem, rooted in this physics of complex systems, how should my practice be structured differently on Monday? We need actionable steps.
Practice has to be completely redesigned around the constraints-led approach, the CLA, and the concept of representative learning design. Coaches have to transition from being instructors to being architects of learning environments.
So I'm not giving instructions, I'm setting up problems.
Exactly. You channel the learner's self-organization by setting up problems constraints that require an adaptive, viable solution. So instead of isolated, repetitive passing to a static target, you implement a small-sided game
With a rule.
with a constraint, like the ball must change possession every 5 seconds, or the pass has to be completed within 10 yards of the goal. This forces the dynamic systems of your players to reorganize their movement, their perception, and their decision-making all at once to solve that specific problem.
What's the real difference between simple progression and constraint manipulation? I hear those terms used interchangeably, but they feel very different in this context.
They are fundamentally different. Progression usually just implies a linear addition of load or difficulty. Moving from a lighter weight to a heavier one or just adding more volume, it's a scalar increase.
More of the same.
Right. Constraint manipulation involves altering the task, environment, or individual factors to induce adaptation, to force the athlete to discover a functional technique that works for that specific situation. It's about altering the boundary conditions to force a phase transition to a more stable, complex pattern. You are changing the problem itself.
So more scrimmage time is progression.
But changing the number of players from 11 aside to 3 aside or changing the offside rule, that's constraint manipulation. You're changing the rules of the game to force a specific self-organization pattern to emerge.
Okay, how do I program strength training if the goal is transfer and not just maximizing numbers in the weight room, which is the current religion?
You program for transfer by making sure that re-strengthened muscle is reintegrated into the full movement context as early and as functionally as possible. Strength training in this model is really about expanding the athlete's capacity to tolerate mechanical constraints.
So the heavy squats are still important.
They're important for general force capacity, but you have to move quickly into tasks that demand dynamic coordination. Loaded single-leg hops, resisted rotational movements, carries on unstable surfaces.
You're expanding the system's force capacity, then immediately stressing the coordination pattern required to apply that force in a variable representative task.
That's it. A runner might squat 500 pounds, but if they've only practiced moving that force linearly and vertically, their system might not know how to dynamically coordinate the horizontal force application they need for acceleration on the track. Training has to address the coordination pattern as much as the isolated force output.
What's the homeokinetic definition of overtraining? Is it just too much load, or is it something more systemic?
It's the loss of adaptive capacity. The system has been pushed so hard and so repetitively that it loses its ability to generate functional variability. Its resilience declines, and it often defaults into a rigid, energy-intensive coordination pattern that's prone to collapse, either injury or a slump.
So how do we build athletes who self-organize under pressure instead of just executing pre-rehearsed scripts?
To build self-organization, practice has to allow and even encourage movement variability. You have to foster the athlete's own error detection and correction processes. The coach has to step back from the constant prescriptive cues and implement guided discovery.
So when the athlete misses the target,
The coach provides only outcome feedback. The pass was too slow to get through the window, not prescriptive feedback like, you need to step through with your left leg.
and that forces the athlete to solve the problem themselves.
It forces their complex system to find its own necessary adjustment based on the perceived relationship between its action and the environment. It promotes deeper, more adaptable learning. It requires the athlete to become the controller of their own degrees of freedom.
Okay, this is where we might blow some minds. The traditional image of a coach is the general, the director, the master of all answers.
The keeper of the technique manual.
Right. What if my job isn't to give answers, but to shape the environment so athletes discover better solutions themselves?
That is precisely the required shift in pedagogy. The coach moves from being the director to being an architect of learning environments and a facilitator of awareness. You use constraint manipulation to channel behavior, relying on the inherent self-organization tendencies of the complex system that is your athlete.
So I'm trusting the system.
You are. You rely on guided discovery and constraints-led design because you understand that the athlete needs to become attuned to information in their environment to regulate their own movement. The solution isn't in your head, it's emergent in the task.
Okay, so give me the decision tree. When should I use explicit cues versus guided discovery versus constraints-led design?
For skill acquisition, the hierarchy should always favor constraints-led design and guided discovery. They maintain that perception-action coupling and encourage functional variability.
So constraints-led is the default.
It's the default. Design the drill so the solution is obvious without you saying a word. If you want a player to use the inside of their foot for a tight pass, you put a defender so close that only an inside foot pass is even viable.
And if that doesn't work?
Guided discovery is your backup. Provide only outcome feedback, the ball was too high, which forces the athlete to search internally for the solution.
And explicit cues.
Explicit cues telling an athlete exactly how to move their shoulder should be used very sparingly. Maybe to draw attention to a critical element for a total beginner, or in a high-pressure timeout where time is short. But heavy reliance on explicit cues, it risks overriding the athlete's natural self-organization processes. It makes them brittle and dependent.
How do I coach decision-making without turning practice into a classroom lecture on tactics?
Decision-making is movement organization. You coach it by manipulating informational constraints. You don't lecture on tactics. You create game situations that force tactical decisions to become viable solutions.
So if I want my players to attack the center of the field,
You implement a rule that only goals scored from the central corridor count for points. The environment immediately forces the system to reorganize its perception. Where are the gaps? And its action. How do I move the ball there? The decision to attack the center is no longer a conscious command. It's the inevitable emergent solution to the constraints of the task.
What does learning look like in a complex system? Is it fewer errors, or is it faster error recovery?
It is definitively faster error recovery. If you force the system to have fewer errors too early, you risk creating rigidity. True, deep learning means the system has developed robust synergies that allow it to detect and correct deviations rapidly when the environment shifts.
So if I overcoach, am I just making the athlete dependent on me for their organization?
You are 100%. Overcoaching provides external organization. You're basically giving the athlete a pre-programmed script. The danger is twofold. First, you might be forcing them into a coordination pattern that isn't optimal for their unique system.
And second,
When that external cue your voice, the sterile practice environment is removed, or the environment changes in a game, the athlete's system has never learned how to self-organize the solution internally. They are dependent and brittle. They can't detect and correct their own errors when the game state changes.
so what does operational autonomy mean? What do athletes own on a daily basis in a system that trusts self-organization?
Autonomy means the coach owns the problem and the athlete owns the solution. Since every athlete is a unique dynamic system, different limb lengths, different speed profiles, there is no one-size-fits-all technique.
So operationally,
It means you provide the task goals. Get the ball through this window of space. But you allow the athlete total ownership over how they achieve it. They own the movement variability, the exploration, the self-correction. The coach owns the environmental architecture and the constraints that channel the athlete toward highly viable solutions.
all right, let's bring in the skeptical coach who feels like their entire identity, which is built on knowing the one right way to move, is being threatened right now.
It's a real and valid feeling.
So are you saying most technique coachings is overrated? If variability is normal, does that mean standards don't matter?
Technique coaching is reframed, not eliminated. And standards absolutely matter. But the standard has to shift. The standard is performance viability. Does the skill achieve the goal reliably under pressure? Not mechanical consistency. Does it look exactly like the textbook video?
So we're not chasing a single optimal form.
We're replacing that with the pursuit of an optimal range of viable solutions. The standard is flexibility within the boundaries that produce success. A mechanistic regimen that enforces exact repetition makes an athlete rigid. The standards should apply to the outcome and the systemic resilience, not the precise process.
Okay, but this sounds like it could be an excuse for being disorganized. Let the athletes do whatever they want. How do we keep discipline and accountability without the training just turning into chaos?
That's a classic misunderstanding of complexity. The system self-organizes into coherent functional patterns under interacting constraints. Discipline and accountability are maintained by setting clear, challenging task constraints.
The rules and goals.
Right. The rules, goals, and desired outcomes that channel behavior toward effective solutions. You're not imposing explicit organization on their movement. You're imposing constraints that are so tight that the system is forced to self-organize the most effective internal pattern. If the training environment feels chaotic, the coach has failed to set clear channeling constraints.
So accountability is tied to solving the problem, not following my instructions.
Exactly.
So where's the line between emergent learning and just lack of fundamentals?
The line is viability and the scale of the problem. Emergent learning allows the system to find diverse functional solutions for a complex task, like finding a new way to defend a pick and roll. A lack of fundamentals means the system fails to assemble any stable functional movement pattern that achieves a basic pass goal.
So if they can't even make a simple pass.
If, in your small-sided game, they still cannot consistently strike the ball accurately, a fundamental task, then the constraint needs to be temporarily simplified to channel the system into stabilizing that basic functional movement. It's about diagnosing whether the failure is a breakdown in high-level coordination or a breakdown in fundamental capacity.
Okay, show me the causal leverage. What do I change tomorrow that it wasn't changing before? Is homeokinetics predictive, or is it just descriptive after the fact?
The causal leverage is constraint manipulation. That's what you change. Tomorrow, you change your practice design to be more representative of competition. You do not accept a drill that decouples perception and action. You add a live defender to a drill that previously had cones. You change the rule set of your small-sided game to force a specific tactical problem.
That's a direct intervention.
It's a direct causal intervention into the ecology of the practice environment. and it leads to a predictable response in the athlete's organization. And yes, the framework is predictive. It predicts the failure of rigid technique when environmental constraints change. It predicts that changes in control parameters, like pressure or speed, will lead to those predictable emergent phase transitions without external instruction. It predicts what will become unstable and what new patterns might emerge.
But if everything is a system, does anything become unfalsifiable? What are the limits of this framework?
That's a powerful, critical question. The framework is falsifiable through its predictions about stability and variability. If we observe that increasing a control parameter, like speed, does not lead to an expected phase transition, or if we see that functional variability does not correlate with improved viability under stress, then the model has to be refined.
And its limits.
The limit is that it's computationally demanding. We can describe the emergent behavior, but mathematically modeling and predicting the precise moment and form of every phase transition remains incredibly complex, which is why the coach still has to use guided discovery and trust the system's ability to self-organize. You guide the system. You don't micromanage its thermodynamics.
All right, the ultimate measure for any coaching system is performance and return on investment. What does this homeokinetic ecological approach do best? Reduce injuries, improve transfer, or improve consistency under stress?
It excels most powerfully at improving transfer and consistency under stress. By maintaining that perception-action coupling and incorporating the informational stressors of the game in practice through representative design, the coordination patterns learned are viable when the stakes are highest.
So it directly reduces the practice hero game ghost phenomenon.
It does, because the system learns to assemble the right movement pattern based on real game information, not based on the static cues of the training environment. The skills learned are robust because they were forged under conditions that mirror competition's inherent stress and variability.
This nested systems view also seems critical for rehabilitation. How does this change return to play decisions? What kind of stability do we need before we expose them to competition again?
It revolutionizes rehab by moving away from isolating weak parts toward task-oriented training. After an injury, the goal is not just to isolate and strengthen a single muscle, but to reintegrate that new capacity into the full functional movement context.
So rehab specialists should be using movement variability as a tool.
Absolutely. Instead of having a patient walk perfectly straight on a treadmill, they should leverage varied walking surfaces, different visual feedback, balance challenges. This forces the damaged nervous system to actively rediscover stable, adaptable solutions.
So return to play stability is achieved when?
Not when the athlete can execute one perfect rep in the clinic. It's when they demonstrate functional variability, the ability to adjust, maintain viability, and efficiently recover from errors across a wide range of high-level task constraints, like cutting rapidly under fatigue or responding to an unpredictable opponent. The system has to regain the integrity of that perception-cognition-action loop in the actual environment of play.
How does this focus on self-organization affect team culture?
Yeah.
Buy-in, accountability, athlete ownership.
It creates a culture of informed ownership and problem solving. Athletes move from being passive recipients of instruction to active agents who understand they have to explore and adapt. Buy-in increases because the constraints-led approach naturally makes practice more engaging and representative of the actual game.
And accountability shifts.
It shifts from "did you follow my instructions" to "did you solve the problem and maintain viability under the constraints I imposed?" This empowers the athlete to be self-aware and constantly searching for a better, more resilient solution.
So the long-term payoff is an athlete who is more robust against the unforeseen.
Absolutely. The system is resilient because it is flexible.
So what does this all mean? We started by challenging that mechanistic view of the athlete, that brittle paradigm of just levers and pulleys. Arthur Eibroll's homeokinetics, combined with ecological dynamics and dynamical systems theory, it delivers a really powerful rebuttal to reductionism.
It really does.
We learn that movement is a fluid, contextually shaped process. It's more like a dynamic ecology or a flowing field constantly managing energy than it is a static assembly of parts.
And the takeaway for you, the practitioner listening, is that you have to nurture the entire system, brain, body, and environment in unison. By adopting this complex systems paradigm, you prepare movers not just to execute a skill they learned by rote, but to innovate and evolve their skills, their coordination patterns, in the face of whatever chaos and opportunities the competitive world throws at them.
It transforms the athlete from a follower of instructions
Into an active, resilient problem solver.
And that leads to this final provocative thought for you to chew on. If our movements are governed by these deep physical principles, all the way from cellular thermodynamics up to social context, does embracing this complexity mean we must also embrace the inherent unpredictability of high-level performance, knowing that the greatest, most clutch moments of athleticism are always a function of the system self-organizing at the very edge of stability? Maybe the champion is just the one who can ride that chaos the longest.
A thought to end on.
Thank you for joining us for this deep dive into the adaptive athlete. We'll see you next time.